Black holes are among the most fascinating and mysterious objects in the universe. Their very nature defies our conventional understanding of physics and challenges our perceptions of space, time, and matter. These objects are formed when a massive star collapses under its own gravity, creating an incredibly dense region of space where the gravitational pull is so strong that nothing, not even light, can escape. The concept of a black hole, though rooted in Einstein's general theory of relativity, was only fully realized after decades of theoretical work and observational breakthroughs. Understanding black holes involves delving into a complex array of ideas ranging from gravitational theory and quantum mechanics to the broader structure of the universe itself. A black hole's most defining characteristic is the event horizon, the boundary beyond which nothing can escape its gravitational grip. This boundary represents the point of no return. Once an object crosses it, it inexorably falls toward the singularity at the center of the black hole. The singularity is a point where gravity becomes infinite, and our current laws of physics break down. The precise nature of what happens at the singularity remains one of the greatest unsolved problems in physics. It is thought to represent a region where matter is crushed to infinite density, creating an environment where space-time is warped beyond imagination. The formation of a black hole typically begins with the death of a massive star. Stars are essentially massive balls of gas undergoing nuclear fusion, a process where hydrogen atoms fuse to form helium, releasing an enormous amount of energy in the process. This energy creates an outward pressure that counters the inward pull of gravity. However, when the fuel in the star's core runs out, this balance is disturbed, and gravity wins. The core of the star collapses inward, and if the star is sufficiently massive, the collapse continues until a black hole forms. In these cases, the star's outer layers are often expelled in a violent explosion known as a supernova, which can outshine an entire galaxy for a brief period of time. There are several types of black holes, distinguished by their size and the mechanisms of their formation. Stellar black holes, the most common type, are formed by the collapse of individual massive stars, and typically have masses ranging from a few to a few tens of solar masses. Supermassive black holes, on the other hand, are found at the centers of most galaxies, including our own Milky Way. These behemoths can have masses ranging from millions to billions of solar masses, and likely formed early in the universe's history, although their exact origins remain an area of active research. Intermediate black holes, with masses between stellar and supermassive black holes, are theorized to exist but have proven difficult to detect. Primordial black holes are a speculative class of black holes that might have formed during the very early universe, shortly after the Big Bang, due to high-density fluctuations. A black hole's properties are largely determined by its mass, spin, and electric charge, though most black holes in the universe are assumed to be electrically neutral. The study of black holes has led to the discovery of a profound relationship between space and time, as encapsulated in the no-hair theorem. According to this theorem, the only observable characteristics of a black hole are its mass, charge, and spin. All other details, such as the specific makeup of the collapsing star or the original state of the matter, are lost to the universe once they pass the event horizon. This principle underscores the strange nature of black holes. They are regions where the usual laws of physics, particularly our understanding of information, cease to operate as we understand them. The boundary of a black hole, the event horizon, is not a solid surface. Instead, it is a mathematical surface that represents the point at which escape velocity exceeds the speed of light. The concept of escape velocity is central to understanding black holes. In ordinary objects, escape velocity is the speed required to break free from the object's gravitational field. For Earth, this velocity is about 11.2 kilometers per second. However, as we approach a black hole, the escape velocity increases and eventually becomes greater than the speed of light, a situation that no known object can escape. One of the most remarkable aspects of black holes is their effect on space-time. General relativity predicts that a massive object will warp the fabric of space-time, and this distortion becomes more extreme as the object becomes more massive and compact. Near the event horizon of a black hole, space-time is so warped that time itself begins to slow down. From the perspective of an outside observer, any object falling into a black hole will appear to slow down as it approaches the event horizon, eventually seeming to freeze in place. This is a result of the extreme warping of time and space near the black hole, known as gravitational time dilation. To the object itself, however, it would pass through the event horizon without any unusual experience, although it would eventually be torn apart by tidal forces in the process known as spaghettification, if the black hole is sufficiently small. Although the presence of black holes is largely theoretical, there is now strong evidence for their existence. The first indirect detection of a black hole came in the 1960s, when astronomers noticed strange X-ray emissions from certain regions of the sky. These emissions were thought to come from matter being heated to extremely high temperatures as it spiraled toward a black hole. In the decades since, the study of these X-ray sources has provided much of the evidence for the existence of stellar mass black holes. A breakthrough came in 2015 when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first gravitational waves produced by the collision of two black holes. This discovery provided further proof of their existence and opened up an entirely new way of studying these mysterious objects. In 2019, the Event Horizon Telescope, EAT, collaboration made a groundbreaking achievement by capturing the first-ever image of a black hole located in the galaxy M87. This image, though blurry, showed the shadow of the black hole's event horizon against the bright backdrop of the hot gas surrounding it. This was a historic milestone in the study of black holes, as it provided the first direct visual evidence of their existence and confirmed many of the predictions made by general relativity. While black holes have fascinated scientists and the public alike, they also present significant challenges to our understanding of the universe. One of the most famous issues is the information paradox, which arises from the apparent conflict between quantum mechanics and general relativity. According to quantum mechanics, information about the physical state of a system cannot be destroyed, but general relativity predicts that all information falling into a black hole is lost to the universe. This paradox has led to much debate and various hypotheses about how information is preserved, or what happens to it in the extreme conditions of a black hole. Some theories suggest that information might be stored on the event horizon in a manner similar to a hologram, a concept known as the holographic principle. Others suggest that quantum effects near the event horizon might allow information to escape in subtle ways that have yet to be fully understood. The study of black holes also raises profound questions about the ultimate fate of the universe. Black holes grow over time as they accrete matter from their surroundings, and this growth could potentially lead to the formation of supermassive black holes that dominate the centers of galaxies. Over incredibly long timescales, these black holes might continue to grow, possibly even merging with one another, creating supermassive black holes that could eventually dominate the entire universe. However, there is another aspect of black holes that raises deep questions about the future of the universe: Hawking radiation. In the 1970s, physicist Stephen Hawking predicted that black holes might not be entirely black after all. According to his theory, quantum effects near the event horizon would cause black holes to emit a form of radiation, eventually leading to their gradual evaporation. This phenomenon, known as Hawking radiation, has not yet been observed, but it provides a fascinating glimpse into the interplay between quantum mechanics and general relativity.